Welcome everyone to Lecture 10 of Data Analytics Made Easy for Beginners. Today we are entering one of the most exciting frontiers of modern data analytics, the world of text mining. Think about this for a moment. The vast majority of the information that exists in the world today is not stored in neat spreadsheets with tidy numbers. It is stored in words, in emails, in social media posts, in customer reviews, in medical notes, in news articles, and in legal documents. If we cannot analyze text, we are leaving an enormous amount of insight on the table. Today, we are going to learn exactly how data scientists take raw, messy human language and transform it into something a computer can reason about. We are going to look at the fundamental techniques for representing text as data, for measuring the importance of words, and for building predictive models on top of language. By the end of this lecture, you will understand the conceptual foundations of text mining, the industry standard technique called TF-IDF, and how these tools were applied in a real-world case study to predict stock price movements from financial news stories. You will also reflect on the ethical dimensions of text analytics, which are more significant than many people realize. Let me begin by giving you a roadmap of everything we are going to cover today. Looking at page 1, you can see our lecture overview, which lists 7 major sections. We will start with the introduction, specifically the ubiquity and difficulty of text, because before we can solve a problem, we need to deeply understand why it is a problem in the first place. Then we will move into representation engineering, which is the art and science of converting words into numbers. This is the foundational transformation that makes everything else possible. From there, we will study how to measure importance using 2 complementary statistics: term frequency, which we abbreviate as TF, and inverse document frequency, which we abbreviate as IDF. Together, they form what is called TF-IDF, the workhorse of text analysis. After that, we will venture beyond bag of words, because while the basic representation is powerful, there are richer techniques that capture more of the meaning of language. We will then walk through a detailed case study on predicting stock price movement from news text, so you can see exactly how these abstract ideas translate into a real analytical pipeline. We will cover evaluating performance, looking at the specific tools we use to measure how good our text-based models are. And finally, we will address strategic considerations and ethics, because text mining raises profound questions about privacy, fairness, and the responsible use of information about people. That is our plan. 7 sections, each building on the last. Let us proceed. We begin with the question, why does text matter in business? The answer is simple but profound. Text is the most common form of communication in the digital world. Every business, without exception, generates and receives enormous volumes of text every single day. And locked inside that text is some of the most valuable information a business can have. Let me give you 3 categories to think about. The first category is legacy systems. Think about hospitals that have been accumulating medical records for decades, structured notes about patient symptoms, treatments, and outcomes. Think about consumer complaint logs at a utility company, or maintenance and repair records at an airline. This data was generated by humans writing in natural language, and it contains patterns and insights that traditional analytics cannot touch. The second category is modern media. This includes Twitter feeds, Facebook updates, Reddit comments, and blog posts. Social media has created an absolutely unprecedented stream of real-time human opinion. At any given moment, millions of people are expressing what they think, what they feel, and what they intend to buy. If a company can mine that stream intelligently, it gains a window into public sentiment that simply did not exist 20 years ago. The third category is search engines. It is not a coincidence that the most valuable companies in the world, Google, Bing, and others, are built on text-oriented data science. The entire business model of search is about understanding the meaning of a user's words and connecting them to the most relevant documents. That is a text mining problem at massive scale, so the stakes are high. Text is not a niche problem. It is a central problem in modern analytics. Page 3 introduces one of the most important concepts in business analytics, the voice of the customer. Here is the tension that businesses face. On one hand, behavioral data, things like clicks, purchases, and ratings, is quantifiable and easy to analyze. You can put it in a database, run statistics on it, and build models. But behavioral data only tells you what people did, not what they actually think or feel. True customer sentiment is very often locked in unstructured text. When a customer takes the time to write a 3-paragraph review explaining exactly why they returned your product, or when they send a detailed email to customer service describing their frustration, that text contains enormously rich information. It tells you not just that the customer was unhappy, but why, and what specifically went wrong. Product reviews and feedback forms are pure gold for companies that know how to mine them. They contain the vocabulary of customer experience, the exact words and phrases that customers use when they are satisfied or disappointed. And personal communications like emails can reveal detailed, specific customer needs that no survey would ever capture. The challenge, of course, is that there are millions of these documents. No human could read them all. This is exactly why we need text mining, to extract signal from this enormous, messy, valuable resource at scale. We confront the fundamental challenge. Why is text so difficult for computers to analyze? People often call text unstructured data, and in the sense that it does not come in rows and columns, that is correct. But I want to push back on the idea that text is truly unstructured. In fact, text has extremely complex linguistic structure: grammar, syntax, semantics, pragmatics, context. The problem is that this structure is incredibly difficult for computers to parse automatically. Let me describe 3 specific challenges. The first is variable length. A document might be a single tweet of 15 words, or it might be a 100-page annual report. If we want to represent documents as feature vectors and compare them mathematically, we need a way to handle this enormous range of sizes. A matrix of documents by words would have some rows with a few non-zero entries, and others with thousands, which creates computational and statistical problems. The second challenge is messiness. Human beings are not careful writers, especially online. They misspell words constantly. They invent abbreviations. They use slang, emoji, and random punctuation. They write in all caps for emphasis. They switch between languages mid-sentence. None of this is what the grammar book prescribes, and all of it creates noise that our algorithms have to deal with. The third challenge is ambiguity. Language is fundamentally ambiguous. A single word can mean many different things depending on context, tone, and the shared knowledge between writer and reader. This is what makes reading comprehension so effortless for humans and so maddeningly difficult for machines. We will come back to this idea on the next slide. Let's zoom in on one of the most important sources of difficulty in text analysis, the challenge of context. The first problem is synonyms multiple words that share the same meaning. Consider the words big, large, enormous, vast, and gigantic. To a human reader, these are all conveying roughly the same concept. But to a naive text mining algorithm, they are completely different words. If a customer review says the room was enormous and another says the room was huge, a simple word counting approach will not see these as similar, even though they are conveying the same impression. This is called the vocabulary mismatch problem. The second problem is homographs, words that have the same spelling but completely different meanings. The classic example is the word bank. I walked along the bank of the river is about a geographical feature. I deposited my paycheck at the bank is about a financial institution. The letters are identical, but the meanings are worlds apart. A computer reading only the word itself cannot know which meaning is intended without understanding the surrounding context. The third problem is sentiment ambiguity. Consider the word incredible. In everyday speech, we use it to mean amazingly good. That restaurant was incredible. But etymologically, incredible literally means not credible. That is, something so extreme it is hard to believe. Or consider sarcasm. Someone writing, "Oh great, another Monday," is clearly not expressing positive sentiment, even though the word great is there. These layers of meaning are extraordinarily difficult for machines to detect reliably. These 3 challenges, synonyms, homographs, and sentiment ambiguity, are why text mining remains an active research area even decades after it began. We have powerful tools that work well in many settings, but the problems are genuinely hard. Section 2. Representation engineering. We arrive at the conceptual heart of text mining, what we call representation engineering. Here is the core idea. All of the standard machine learning and data mining algorithms that we have studied in this course, classifiers, clustering algorithms, regression models, work on numbers. They require numeric input. They cannot directly consume a paragraph of prose. So the fundamental challenge in text mining is, how do we convert words into numbers in a way that preserves meaningful information? The answer is the feature vector. A feature vector is a list of numbers that represents a document. Think of it as coordinates in a very high-dimensional space, where each dimension corresponds to a possible word or term. Once we have converted every document into a feature vector, we can apply any standard algorithm, a logistic regression, a decision tree, a neural network, and it will work just as if the input had been numeric all along. This transformation from a sequence of words to a feature vector is the foundational step in all text mining. Everything else we discussed today is either about how to do this conversion well or about what to do with the vectors once we have them. Now let us look at the simplest and most widely used approach to building these feature vectors. Now we introduces the bag of words model, which is the most common starting point for text representation and one of the most important ideas in the entire field. Here is the intuition. Imagine you take a document, say a customer review, and you put all the words in a bag. You shake the bag up. Now you no longer know the order in which the words appeared, or the grammar connecting them. All you know is which words are in the bag, and how many times each word appears. That is literally the bag of words model. It treats every document as an unordered collection of individual words. It completely ignores grammar, word order, and sentence structure. If the review says, "The product is excellent, but the shipping was terrible," the bag of words model records product, 1 excellent, 1 shipping, 1 terrible, 1 and so on. It does not know that excellent refers to the product and terrible refers to shipping. Now, you might immediately object. How can something this crude possibly be useful? And that is a completely reasonable reaction. But here is the remarkable empirical fact. The bag of words model is simple, computationally inexpensive, and surprisingly effective across a huge range of practical applications. Spam filters built on bag of words have been extraordinarily accurate for decades. Document classifiers built on bag of words can categorize news articles by topic with very high accuracy. The reason it works, despite ignoring word order, is that topic and sentiment are often communicated through word choice more than through syntax. A document that contains the words merger, acquisition, and shareholders is probably about corporate finance, regardless of how those words are arranged. So always start with the simplest model. Bag of words is that model, and it forms the foundation for everything we build next. Before we can build a bag of words representation, we need to clean and standardize our text. Page 8 walks us through the first pre-processing steps, tokenization and normalization. Tokenization is the process of breaking a raw text string into individual units, which we call tokens. Most of the time, tokens are words, but they can also be punctuation marks, numbers, or even characters, depending on the application. For example, the sentence, "The product arrived late," would be tokenized into "The product arrived late." Each token becomes a candidate feature in our model. Normalization is the process of standardizing these tokens so that superficially different forms of the same word are treated identically. The most basic form of normalization is converting all characters to lowercase. This ensures that apple, apple, and apple, which clearly represent the same word, are counted as the same feature rather than 3 distinct features. Without normalization, our feature space would be bloated with near duplicate terms that add noise without adding information. Think of these 2 steps as the beginning of a data cleaning pipeline. Just as with any data, raw text is messy and inconsistent, and we need to bring it to a canonical form before analysis. Tokenization and normalization are step 1. Now let us look at step 2. Now we introduce the technique of stemming, which is the next step in pre-processing. Here's the problem that stemming addresses. The English language, like most languages, has a rich system of morphology. A single root concept can be expressed through many different word forms. Consider the word announce. In a corpus of news articles, you might encounter announces, announced, announcing, and announcement, all referring to the same basic concept. Without stemming, our bag of words model would treat these as 4 completely separate features, scattering the evidence for a single concept across multiple columns. Stemming solves this by algorithmically reducing every word to its root form, which we call the stem. The most famous stemming algorithm, the Porter stemmer, would reduce announces, announced, and announcing all to the stem announc. Note that this is not a real English word, but that is fine. The stem does not need to be a real word. It just needs to be a consistent base form that consolidates all variants. By stemming, We reduce the dimensionality of our feature space and ensure that all grammatical variations of a word contribute their evidence to a single feature. This typically improves the accuracy of downstream models because the features become more densely populated with evidence. One important caveat: stemming is not perfect. It is a heuristic algorithm, and it sometimes makes errors, merging words that should be distinct, or failing to merge words that should be combined. But the key principle is consistency. As long as we apply the same stemming algorithm at both training time and prediction time, the model will work correctly even if individual stems are slightly malformed. We cover the third major pre-processing technique: stop word removal. Stop words are words that are extremely common in a language, but carry very little distinctive information about the topic or sentiment of a specific document. Examples in English include the, and, of, on, is, it, to, in, that, this, was, for. These words appear in virtually every document, in virtually every corpus. They are the linguistic glue that holds sentences together, but they tell us almost nothing about what a document is specifically about. If we include stop words in our feature set, they will have very high term frequencies across all documents, which means they will dominate our feature vectors. But because they appear equally in all documents, they provide no discriminative power for classification or clustering tasks. Including them adds noise and computational cost without adding signal. So the standard practice is to maintain a list of stop words and remove them from every document during pre-processing. This reduces the size of the feature set, speeds up computation, and typically improves model performance. However, and this is an important nuance, sometimes removing stop words is a mistake. The slide gives a beautiful example, the title On the Road, the famous Jack Kerouac novel. If you remove stop words from this title, you are left with road. You have lost the most meaningful part of the phrase. There are also linguistic tasks, like authorship attribution, where the frequency of function words like the and is actually a useful signal. The lesson is, apply domain judgment. Stop word removal is the right default for most text mining applications, but always think about whether the words you are removing might matter for your specific task. Section 3. Measuring Importance, TF, and IDF. We introduced the first of our two importance metrics, term frequency, or TF. The intuition behind term frequency is simple. If a word appears many times in a document, that document is probably about that word. If the word mortgage appears 40 times in a news article, the article is very likely about mortgages. If it appears only once, the article is probably about something else that happens to mention mortgages in passing. Formally, the term frequency of a word in a document is simply the count of how many times that word appears in that document. So if the word merger appears 7 times in a document, TF of merger in that document equals 7. However, raw counts can be misleading because documents vary enormously in length. A word appearing 7 times in a 50-word document is much more significant than the same word appearing 7 times in a 5,000-word document. To correct for this, we normalize the TF by dividing the word count by the total number of words in the document. This gives us a proportion, the fraction of the document's words that are this particular term, which is comparable across documents of different lengths. Term frequency answers the question, how important is this word within this specific document? But we need to also ask a second question, which term frequency cannot answer? How unique is this word across the entire collection of documents? That is where IDF comes in. Imagine you are building a news article classifier, and your corpus contains thousands of articles from a financial newswire. The word the appears in every single article. So does company, said, billion, and year. These words will have very high term frequencies in many documents, but they are useless for classification because they do not help us distinguish one article from another. An article about a pharmaceutical merger and an article about a retail bankruptcy will both use quote, company and said frequently. For classification tasks, a feature is only useful if it varies across the classes we are trying to distinguish. A word that is equally present in all documents provides no discriminative information. It is like trying to tell people apart by the fact that they all breathe. Technically true, but not helpful. Similarly, for clustering, if every document is rich in common words, the distance or similarity between documents will be dominated by these uninformative terms, and documents that are genuinely similar in topic will not cluster together correctly. We need a mechanism that actively penalizes words for being too common across the entire collection and rewards words that are distinctive and rare. That mechanism is inverse document frequency. We introduce inverse document frequency, or IDF. This is the second component of the TF-IDF formula, and it addresses exactly the problem we just identified. The concept behind IDF is to measure the sparseness of a term across the entire corpus, the full collection of documents. The rarer a word is across the corpus, the higher its IDF score, and the more weight it will receive in our feature vectors. Common words get a low IDF score, rare words get a high IDF score. Let me walk you through the formula carefully. The IDF of a term is calculated as 1 plus the logarithm of the ratio of the total number of documents in the corpus divided by the number of documents that contain that term. Let me break that down. The denominator is documents containing term. This is the count of how many documents in your collection include this word at least once. The numerator is total documents, the overall size of your corpus. We divide total by containing to get the inverse. A large number means the term is rare. A small number close to 1 means the term is ubiquitous. We then take the logarithm of this ratio. Why the logarithm? Because we do not want the scale of IDF to be extreme. A word that appears in 1 out of 1,000,000 documents would get an astronomically high raw ratio. The log compresses this into a manageable range. We also add 1 to the final result to ensure that even a word appearing in every document still gets an IDF of 1 rather than 0, which prevents numerical instability in downstream calculations. So to summarize, a word like the, which appears in every document, has an IDF very close to 1, near 0 boost. A word like subprime, which might appear in only a small fraction of your articles, gets a high IDF, a big boost. This is exactly what we want. Rare, specific words get amplified, common words get penalized. Now we put the two components together to form TF-IDF, the industry standard for weighing text features, and one of the most important formulas in all of data science. The formula is elegantly simple. TF-IDF of term T in document D equals TF of T in D multiplied by IDF of T. Let us trace through what this formula accomplishes. A word gets a high TF-IDF score when, and only when, two conditions are simultaneously true. First, the word appears frequently in this specific document, high TF. And second, the word appears rarely across the broader corpus, high IDF. Words that satisfy both conditions are genuinely distinctive signatures of that particular document. Think about what this filters out. Words that are common across all documents, like the or said, will have low IDF no matter how often they appear in a single document, so their TF-IDF will be low. Words that appear rarely in a document but happen to be rare in the corpus will have high IDF but low TF, so their TF-IDF will also be modest. Only words that are both locally frequent and globally rare will achieve high TF-IDF scores. The practical result is a feature vector that is much more informative and discriminative than raw word counts. Instead of every document looking similar because they all contain the same common words, TF-IDF vectors highlight the terms that make each document unique. This leads to dramatically better performance in classification, clustering, and search applications. TF-IDF was developed in the context of information retrieval in the 1970s and 1980s, and it remains a cornerstone technique today, even as deep learning has introduced more sophisticated alternatives. For many practical business applications, TF-IDF is exactly what you need. We start to look at techniques that go beyond the basic bag of words model. The first of these is n-grams. Recall that the bag of words model completely ignores word order. Most of the time, this is an acceptable trade-off. But there are cases where word order carries critical meaning that we lose when we throw away the sequence. This is where n-grams come in. An n-gram is a contiguous sequence of n words from a document. When n equals 1, we have the standard bag of words, individual words, also called unigrams. When n equals 2, we have bigrams, sequences of 2 adjacent words. When n equals 3, we have trigrams, sequences of 3 words. The example on the slide is beautifully illustrative. The bigram, exceed expectations. If we analyze the words individually, exceed and expectations are both neutral to positive words. But the phrase exceed expectations has a very specific, strongly positive connotation in business English. It means performance that goes above and beyond what was promised. By including this bigram as a feature, we capture that meaning in a way that individual words cannot. Similarly, consider the difference between not good and good. A unigram model sees the word good and registers a positive signal. A bigram model sees not good, and if it has learned the bigram, correctly interprets this as a negative signal. This is why n-grams are particularly important in sentiment analysis. The practical trade-off is dimensionality. Adding bigrams and trigrams to your feature set can multiply the number of features by factors of 10 or more, which increases computational cost and can lead to overfitting on small datasets. So we typically use n-grams selectively when we have reason to believe that word-level context matters for our specific task. Let's introduce named entity extraction, which represents a more sophisticated approach to understanding what is in a document. Rather than treating all words as equivalent tokens, named entity extraction uses algorithms, often pre-trained machine learning models, to identify and classify specific categories of entities mentioned in text. The primary categories include people, organizations, locations, dates, monetary amounts, and product names. The slide gives the example of, quote, Silicon Valley or Apple Inc. A simple bag of words model would see, quote, Silicon, Valley, Apple, and Inc. as 4 separate, unrelated tokens. A named entity extraction system recognizes that, quote, Silicon Valley is a location entity and Apple Inc. is an organization entity, and crucially, it recognizes each as a single, unified concept rather than individual words. This matters enormously in practice. Consider financial news analysis. If you are trying to understand which companies are mentioned in relation to mergers and acquisitions, you need to recognize that Microsoft Corporation, and MSFT are all the same entity. Named entity extraction does this disambiguation and normalization automatically. The slide describes this approach as knowledge intensive, and that is exactly right. These systems require pre-trained models that have learned from vast corpora of annotated text, and they encode substantial world knowledge. Modern systems like Spacey and Stanford NLP achieve very high accuracy on standard entity types, making named entity extraction a practical tool for production text mining systems. We encounter a beautiful and conceptually sophisticated idea: topic models. Up to this point, our representations have been at the level of individual words, but there is an important intermediate level of abstraction: topics. A topic is a coherent cluster of words that tend to co-occur because they are all related to the same underlying theme. A finance topic might include words like, quote, earnings, revenue, profit, quarter, shares. A technology topic might include software, algorithm, platform, cloud, data. A topic model is an algorithm that discovers these themes automatically from the text data, without being told in advance what the topics are. The most famous topic model is called Latent Dirichlet Allocation, or LDA. Given a corpus of documents, LDA infers a set of latent, meaning unobserved topics, and then represents each document as a mixture of those topics. For example, a news article about a technology company's quarterly earnings might be represented as 40% finance topic, 35% technology topic, 15% business strategy topic, and 10% other topics. This mixture representation captures the document's thematic composition in a very compact and meaningful way. The word latent in the title means hidden or unobserved. The topics are not things we define or label in advance. They emerge from the statistical patterns of word co-occurrence in the corpus. This is what makes topic models so powerful. They can discover the underlying thematic structure of a corpus we have never analyzed before. The practical application mentioned on the slide is search. If a user searches for quote, yield in a collection of agricultural and financial documents, a topic model can disambiguate. Are they asking about crop yield or bond yield? By understanding the topical context of both the query and the documents, the search engine can retrieve genuinely relevant results, even when the exact query words do not match the document words, addressing the vocabulary mismatch problem we discussed earlier. Section 5. Case Study. Predicting Stock Price Movement. Now we move from theory to practice with a detailed case study. Can we predict stock price movements from financial news text? The business problem is this. Financial markets react to news. When a company announces a merger, files for bankruptcy, or releases a blockbuster earnings report, its stock price often moves sharply up or down within hours. If we could read news stories and predict which ones are likely to cause significant price movements, we could flag those stories for human analysts, enabling faster and better informed trading decisions. The goal, as stated on the slide, is to recommend news stories likely to cause a price change of plus or minus 5%. Why 5%? Because that is a threshold that represents genuinely actionable volatility, significant enough to matter for trading strategies, but not so extreme that such events are too rare to model effectively. One critical challenge is timing. The market reacts very quickly to news, often within minutes. So we have to be careful about how we align news timestamps with price windows. A news story published at 9 a.m. might be reflected in prices by 10 a.m. We must ensure that our training data does not inadvertently use price information from after the news was published to predict price changes as if we were reading the news in real time. This temporal constraint is a subtle but crucial aspect of any financial prediction system. Finally, we simplify this into a binary classification task. Either there is a significant price change, a move of plus or minus 5%, or there is not. This turns a complex prediction problem into a manageable yes-no question that our standard classifiers can address. Next, we look at the actual data pipeline used in this case study. The first step is alignment, synchronizing the news data with the price data. Specifically, the researchers used open and close prices at specific times, 10 a.m. and 4 p.m. A news story published before 10 a.m. would be linked to the 10 a.m. opening price and the 4 p.m. closing price. The label change or no change is determined by whether the stock moved more than 5% between those two time points. This temporal alignment is done carefully to avoid any look-ahead bias. The second step is text preparation. The raw dataset contains 36,000 news stories. Each story goes through our pre-processing pipeline: tokenization, lowercasing, stemming, and stop word removal. Then each story is converted into a TF-IDF feature vector. The result is a matrix with 36,000 rows, one per story, and thousands of columns, one per unique term in the vocabulary. The third step is modeling. Two classic machine learning classifiers are applied to this feature matrix: naive Bayes and logistic regression. You have encountered both of these classifiers in earlier lectures. Here, they receive the TF-IDF vectors as input and are trained to predict the binary label, significant price change or not. This is a beautiful example of the complete text mining pipeline: raw text, pre-processing, feature extraction, model training, and evaluation. Each step follows logically from the last, and the whole pipeline can be automated and applied to new stories in near real time. Now we present the results, and they are very illuminating, not just in terms of performance, but in terms of what the model has learned. One of the most valuable things about interpretable models like naive Bayes and logistic regression is that we can examine which features, which words the model has learned are most predictive. This is measured using a concept called information gain, which quantifies how much each feature reduces our uncertainty about the class label. The slide shows the words with the highest information gain for predicting significant stock price movement. They include merger, acquisition, lawsuit, and outperform. Think about why these make perfect intuitive sense. When a company is involved in a merger or acquisition, the stock price almost always moves dramatically, either up for the target company or down if the acquirer is seen as overpaying. A lawsuit filed against a company can create enormous uncertainty and typically causes the stock to drop. And analyst upgrades using the word outperform are well-known market catalysts. These words are serving as evidence for market volatility. They are the financial equivalent of red flags, linguistic signals that something significant is happening that the market will react to. The performance results are also striking. Simple models achieve twice the precision of random guessing for the top 20% of stories. This means that if you applied this model and only acted on the stories it flagged as likely to cause significant movement, you would be right twice as often as chance. In a domain as noisy and competitive as financial markets, that is a very meaningful advantage. Section 6. Evaluating performance. We look at how we measure whether two text documents are similar to each other, an important capability for search engines, recommendation systems, and document clustering. Once we have represented documents as feature vectors in a high-dimensional space, we can use standard geometric concepts to measure similarity. The most common measure for text vectors is cosine similarity. Here is the intuition. Two documents represented as vectors can be thought of as arrows pointing in directions within the high-dimensional word space. If two documents are about the same topic, their vectors will point in roughly the same direction. They will contain many of the same words with similar frequencies. Cosine similarity measures the cosine of the angle between two vectors. A value of 1 means the vectors point in exactly the same direction and the documents are maximally similar. A value of 0 means the vectors are perpendicular and share no common content. Critically, cosine similarity is invariant to document length. A short and a long document about the same topic will have similar cosine similarity, even though their raw word count vectors might be very different in magnitude. This is exactly the property we want, because a 2-paragraph summary and a 10-page report about the same merger should be recognized as similar. In a search engine context, cosine similarity is used to rank how well each document in the corpus matches a user's query. The query is itself converted into a TF-IDF vector, and every document's similarity to that query vector is computed. Documents are ranked from highest to lowest similarity, and the top results are returned to the user. This is, in simplified form, how Google search and similar systems work at their core. Now we discuss how to evaluate the performance of our text classification models using the same tools we apply to any classifier. The two main visualization tools covered here are ROC curves and lift curves, both of which you have encountered earlier in this course. The ROC curve, which stands for receiver operating characteristic, plots the true positive rate against the false positive rate at different classification thresholds. In our stock prediction example, the true positive rate is the fraction of genuinely high movement stories that our model correctly flags. The false positive rate is the fraction of low movement stories that our model incorrectly flags as high movement. A perfect classifier hugs the upper left corner of the ROC plot. A random classifier produces a diagonal line from lower left to upper right. The area under the ROC curve, AUC, provides a single number summarizing overall classifier quality. A lift curve is particularly useful in business contexts where we are not evaluating the entire dataset, but only a top fraction. The lift curve shows how much better the model is than random guessing when we take the top X% of stories by predicted probability. In the stock case study, the model showed a lift of 2 in the top 20%, meaning if we flag the 20% of stories with the highest predicted probability of movement, we capture twice as many true movers as we would by random selection. These evaluation tools are not specific to text mining. They are general tools for binary classification, but they are particularly valuable in text mining applications because our datasets are often large, class imbalanced, and operationally, we are usually interested in the top of the ranked list rather than the entire output. Section 7, Strategic Considerations and Ethics. We step back from the technical details and think about text mining as a strategic capability for organizations. The first key insight is data as a strategic asset. If your company has accumulated years of text archives, customer emails, service call transcripts, legal correspondence, internal reports, that archive is not just a storage problem, it is a potential gold mine. Organizations that have learned to mine their text archives can extract competitive intelligence, identify operational patterns, predict customer behavior, and surface risks that would be invisible from purely numeric data alone. The concept of building proprietary vocabularies is particularly interesting. In niche industries, pharmaceuticals, semiconductors, specialty manufacturing, the language used by experts is highly specialized. A generic text mining model trained on general news will perform poorly in these domains because it does not understand the terminology. But a company that takes the time to build a domain-specific vocabulary, curating stop words, stemming rules, and entity lists appropriate to their industry, develops a text mining capability that competitors cannot easily replicate. This specialized knowledge becomes a proprietary asset. Finally, text mining is often described as a competitive frontier. Many industries are still at the stage where behavioral data, transactions, clicks, purchases is analyzed carefully, but the enormous volumes of text data are left largely untouched. Companies that invest in text mining capabilities now are positioning themselves ahead of a wave that will eventually sweep every industry. let's address a topic that I feel very strongly about and that you must take seriously as a data analytics professional: the privacy and ethical dimensions of text mining. Text mining is different from mining numerical transaction data in a critical way. Text is deeply personal. When people write emails, messages, reviews, or medical notes, they are expressing their thoughts, feelings, and experiences in their own words. Mining that text, even with the best analytical intentions, raises profound ethical questions. The first issue is anonymization. Many practitioners assume that if you remove names from a dataset, you have protected privacy. But this is often not true for text data. A patient's medical notes might describe very specific symptoms, medications, and life circumstances that make that person uniquely identifiable to someone who knows them, even without the name attached. Legal documents, emails, and financial records can contain combinations of details that effectively identify individuals even after traditional anonymization. This is called re-identification risk, and it is a serious concern in text mining. The second issue is sensitive information. Text often contains information that people would consider extremely private: health conditions, financial struggles, relationship difficulties, religious beliefs, political views, and mental health challenges. If this information is mined and used inappropriately, for example, to discriminate in employment, insurance, or credit decisions, it can cause real harm to real people. The third issue is policy navigation. As a data scientist, you will often find yourself at the intersection of what is technically possible and what is ethically appropriate. The fact that you can mine a corpus of customer emails does not mean you should, or that customers would consent if asked. Building ethical text mining systems requires actively thinking about consent, data minimization, purpose limitation, and the potential for harm. My strong advice: always ask not just can we do this, but should we do this, and how should we do it responsibly? Conclusion? We reached the conclusion, and I want to leave you with the most important takeaway from today's lecture. Successful text mining requires the right analytical mindset, not just the right algorithms. The first principle is problem formulation. Before you choose a technique, before you write a line of code, you need to deeply understand what business problem you are trying to solve. Are you classifying documents into categories? Extracting information about specific entities? Finding similar documents? Predicting an outcome from text? The answer shapes every decision that follows. Which pre-processing steps to apply, which representation to use, which model to train, and how to evaluate success. The second principle is to start with the simplest model. This is a theme that runs through all of data analytics, not just text mining. The bag of words model is crude and makes many simplifying assumptions, but it works remarkably well across a wide range of applications. Do not immediately jump to complex deep learning models or topic models unless you have evidence that the simpler approach is insufficient. Simpler models are faster, cheaper, more interpretable, and easier to maintain. The third principle is to add complexity only when the business task demands it. N-grams capture phrase-level context. Named entity extraction identifies real-world entities. Topic models discover latent themes. Each of these adds complexity. Each should be added only if you have a clear reason to believe it will materially improve performance on your specific problem. Complexity for its own sake is the enemy of good data science. The fourth and most fundamental principle is to always connect the technical representation back to the business goal. Every choice you make in your text mining pipeline, your vocabulary, your stop word list, your TF-IDF weighting, your model, should be defensible in terms of what it does for the business outcome. You should always be able to explain, in plain language, why each choice helps you better predict, classify, or understand whatever the business cares about. And finally, let me summarize the 4 core messages from today's lecture. First, text is ubiquitous but messy. It is the most common form of human communication in the digital world. It is rich with insight, and it is genuinely difficult for computers to process because of variability, messiness, and ambiguity. Second, representation engineering is the key transformation. The entire enterprise of text mining rests on the ability to convert sequences of words into numeric feature vectors that standard machine learning algorithms can consume. Tokenization, normalization, stemming, and stop word removal are the essential pre-processing steps that make this possible. Third, TF-IDF is the core tool for word weighting. It elegantly combines the local frequency of a term within a document with the global rarity of that term across the corpus. Words that are both locally frequent and globally rare receive high TF-IDF scores, and these are exactly the words that carry the most distinctive information about each document. Fourth, data analytic thinking turns raw words into predictive power. The case study on stock price prediction showed that even simple models, naive Bayes and logistic regression applied to TF-IDF vectors of news text, can achieve performance significantly better than chance. The key was applying systematic analytical thinking, aligning data correctly, choosing appropriate features, selecting suitable models, and evaluating rigorously. That is everything for Lecture 10. I hope this has opened your eyes to the enormous world of text analytics and given you a solid conceptual foundation to build on. In the weeks ahead, we will continue to develop your analytical toolkit with new topics and new case studies. Thank you for watching, and I will see you in the next lecture.